So we are exploring the third unit in Chapter 9 under measurement. And so in this unit, we're going to be looking at measuring weights and temperature. So two more quantities in which we often associate with measurement. All right, in this unit, or in this section at least, we're going to apply the metric prefixes to units of weight. We'll talk about converting weights within the metric system. By now, I hope to see a comparison or a contrasting similarity between how we were doing with linear distances and then the idea also with weights. And so hopefully that doesn't feel I want to say like esoteric or so, unfamiliar. Hopefully the process of using the unit conversion is starting to make a little bit of sense, and that the process of converting from one unit to another doesn't feel so foreign. In the third part, we're going to look at relationships between volume and weight within the metric system, and then using dimensional analysis to change units of weight to and from the metric system, and then understand the temperature scales. Okay. So in that regard, like knowing what the names are and then some common ideas of what various temperatures are familiar to us and what they look like, sound like uh, underneath. Okay, all right. Weight and mass. There are two different ideas here. A weight, like if you say that you are, I don't know, 150 pounds, that's not your mass, that is your weight. That is the gravitational effect on your mass. And so that's often confused or overlooked, and we kind of use them as synonyms. Oftentimes when we are in just speaking with our friends, for example, we'll often refer to our weight when we mean our mass and vice versa. Okay, but it's realized that in a academic setting or a more formal setting, for example, there is a significant and important difference between these two. For example, if you were on the moon, your weight would be different, but your mass would be the same. Okay, the gravitational force on the moon is about a sixth that it is here on Earth. So let's say you weighed 150 or well, 150 pounds here on Earth. That means that in the moon, we divide that by 6, you'd be 25 pounds on the moon. So you would have a much less weight, even though your mass would be the same. Mass is the measurement of stuff, of how much stuff you have, uh, typically referring to like the quantity of matter and its molecular structure. Or let me say that a better way. Your matter is determined, how much matter you have is determined by your molecular structure. Okay, and that's the thing that determines what we call mass. Okay, moving on then, the unit of weight in the English system is, we have ounces, which can be confusing with the fluid ounces and ounces of volume we mentioned earlier. 16 ounces per 1 pound. And then there are 2,000 pounds forms a ton in the English system. Typically, we think of like tonnage. You'll see that with referring to cars as a common example. I was trying to think of other. So I think the one that stands out the most to me is when I'm in a or I'm at a like a bridge. If you've ever been to like on a bridge, for example, you'll see a sign often saying like the weight allowance of the bridge, or that's allowed on the bridge. That's in reference to your car weight, and so you want to be careful about not exceeding that tonnage. Otherwise, it will be a bad day for you. Okay, so let's move on here then. So the metric system has these measurements of weight. We have the kilogram, um, we have the hectogram and decagram. And again, these, for whatever reason, we don't frequently use those measurements. Definitely use grams. And the decigram, I don't know if it's used a whole lot. I don't come across it very much. But the centigram and milligram, you certainly will. Especially, I was thinking like in like the medical field, I often hear those. Or anytime you're measuring something that's really like really light. So if you're doing any kind of lab or something like that, these really come into play there. All right. So a gram is really light anyways, but these sensitive measures are like if you ever wondered like how much does a paperclip weigh, right? That would be measured probably in milligrams. Okay, because it's very light. All right. So an example of changing the units within the metric system. So say we want to go from 950 milligrams to grams. Okay, so what do we have here? Well, milligrams are a very small measure, and we want to move to grams, which is a very big measure. Okay, so if we want to talk about 950, so I'm going to use this analogy just to kind of show the comparison. This is a gram, and this is 0. So for every 1 gram, right? If we go back up here, for every 1 gram, there are 0.0001 grams, right? Or another way of saying that is that there are 1 over those. So there's 1,000 grams, which is I need 1,000 of these little marks. And you may think I'm measuring distance here, but you can think of this as like units on a scale, right? So like think about getting your weight measurement, right? And so these are like the little decimal points on a digital scale, or if you have a analog scale, you'd actually see these physical measurements. And so I have 1,000 of these, right? And so there's 1,000 of these milligrams. There's 1,000 of these little tick marks. And when I get to 1,000, that means I have 1 gram. Okay. And so you can see that's quite a few. I have 950 of them. So that's going to put me like right here. So I'm going to be really close to a full gram, but it's not quite a full gram. And so it's going to turn out to be 0.95 grams. Okay. And the way that we can do that is just like before, we have 950 milligrams. And if I want grams, then I'm going to put milligrams on the bottom. Okay, for every 1 gram, there is 0.001 micrograms. Okay, and so micrograms cancel out. Dividing by 0.0001 is the same thing as multiplying by 1,000. Oh, no, I'm sorry. I did that backwards. I have milligrams and I want grams. Yeah, so I need to reverse this. And if I do that, then you get the desired result. Sorry, I made a mistake there. And what I'm writing, what I'm saying is true, but what I'm writing is wrong. So you have 950 milligrams. And I have 1,000 milligrams per 1 gram. Okay, so that's what I need. And to see that, if we look at this relationship, I want to get rid of, I want grams, right? So I need to move this over to make it milligrams. So mg divided by 0.001 is equal to grams. Okay, so dividing this relationship here, that means that this comes upstairs and it becomes 1,000 milligrams is equal to 1 gram. Okay, and so this is the relationship I'm using. That's what I'm using here. So that's where it's coming from. So that was my mistake. Well, not my mistake, but poorly explaining this. And this part right here was wrong. That was my mistake. Okay, so 950 milligrams. I want to know how many grams are in a milligram. Sorry, how many grams are in a milligram? Yeah, and so it takes 1,000 milligrams to make 1 gram. So I'm going to cancel out the milligrams with the milligrams. I know it looks like I'm canceling through the 1,000, which I wasn't trying to do. Okay. And then I get 950 divided by 1,000, then gives me then the 0.950 that you see here, which is why they say you go backwards 3 decimal places or move the decimal. I'm not a big fan of memorizing things. I kind of want you to understand where they're coming from. So hopefully that makes more sense. Because it's the same process for all of these. You don't need to memorize a bunch of different relationships if you just recognize how to transfer between the bigger units to small units and vice versa. Okay. Next example, volume and weight in the metric system. I have 1,000 cubic centimeters. It's equal to one, forget that, is that decameter? Decimeter. Is that what that? No, it's decigram. Let me go back up here. Which one was that? Oh, must have been from the other day. Okay. That's 1 cubic liter, which is 1 kilogram. Maybe it's down here. Yeah. Okay. So I forget what the DM cubic DMs are. It's in the other measurement for volume. Let's go look real quick. Just because I feel unsatisfied without knowing. Was that this one? One. What was it? Deca? Yeah, so it had to be this one, right? DL's deciliter. Probably lost you in your interest. Sorry about that. Something about leaving it unanswered is unsatisfying for me. So let's see. Well, DN. Okay. Well, I feel like we ran across it, but man, I'm not seeing it. Okay. Well, whatever that particular value is, hmm, it's 1,000 of. And okay, and so we have 1 liter is equal to 1,000 or 1 kilogram, and 1 liter. Sorry, I said 1,000. I was looking at this. 1 liter is equal to 1 kilogram, and 1 cubic meter is equal to 1 kiloliter, which is equal to 1,000 kilograms or 1 ton. So this measurement here is different in weight and tonnage than. So there are different measurements for that. So just be clear about when they refer to tons. All right, volume and weight in the metric system. So an aquarium holds 0.25 cubic meters of water. How much water does it weigh? Okay, we use the fact that 1 cubic meter of water is 1,000 kilograms. And so if we do that connection, then we have, uh, remember, 1 cubic meter of water. So this is just to kind of give you an idea, that's 1 meter by 1 meter by 1 meter. So imagine a cube like this, be a very shallow swimming pool, but uh, I don't know if that's going to make it look any better. But it's a box of water, right? So with one with one with 1 meter on each side. So this is a meter, that's a meter, and then it's a meter this direction. So each one of those is 1 meter, and that weighs or has a mass of 1,000 kilograms. Okay. And so multiplying then 0.25 cubic meters, the cubic meters cancel and we're left with 1,000 kilograms. And multiplying that by the 0.25 gives us 250 kilograms. Okay, so it's a pretty significant weight. 250 kilograms is pretty heavy. If you ever carried water, you'll know that it feels really heavy, and that's why. All right, English and metric equivalents. 1 ounce is 28 grams. 1 pound is 0.45 kilograms. And 1 ton is about zero point 0.4 tons. And fortunately, they're named the same, even though their spellings are different. But you'll also notice the relationships are different. So 1 ton, remember, that's 2,000 pounds, is 0.9 tons, or let's think kilograms. Okay. Using dimensional analysis, convert 160 pounds to kilograms. Okay, so again, this is what we have, and this is what we want. So we know that there are 0.45 kilograms for every pound. So 160 pounds, and we want kilograms on top. So there's 0.45 kilograms per 1 ton, or per 1 pound, sorry. So the pounds cancel, and we're left with 160 times 0.45, which gives us 72 kilograms. So a person, right, weighs 72 kilograms, and water, a cubic meter of water is 250 kilograms. So that should give you a comparison about that's this is like 3 people, right? It's about roughly 3 people who all weigh 660 pounds. So it's like that'd be like carrying 3 people. So you can see it's pretty heavy, right? Measuring temperature. So things familiar to us, maybe when water freezes, right? If you ever go outside in the wintertime and you see icicles or something like that, or ice cubes in your fridge usually operates right around 32 degrees Fahrenheit, and then water boils at 212 degrees Fahrenheit. Meanwhile, the Celsius system is designed actually built around water. So they make the zero when water freezes, and then when water boils, that's 100 degrees. So it's an extreme range, as you can see from the Fahrenheit scale, going from 32 to 212. It's a much wider system than going from 0 to 100. However, that's the measurement, and that's why oftentimes when you see Celsius temperatures like on the weather, so if you ever go to a foreign country, they typically use Celsius. A very common, like room temperature is usually around 20 degrees Celsius. A little warmer room, maybe like 22 degrees Celsius. Where I live in the summer here, it's usually between like 35 and 41 degrees Celsius during the day, which is pretty warm. And then in the wintertime, it's probably like, I'd say like 12 to like 15 during the day. It can get up to 20, it's not uncommon. That's, like 19 or 20, 19 to 20 during the daytime. And then it can get down to, zero uh, during the coldest parts of winter here. Okay. All right. And then here's the conversion between them. So if you want to go from Fahrenheit to Celsius, you multiply by, so if you're given a Celsius temperature, so like 9.5, let's say if I wanted to know, I said that the common room temperature is 20 degrees. So what is that in Fahrenheit if it's 20 degrees Celsius? So 4 goes into, or 20 goes into 4, 20 goes into, sorry, 5 goes into 20. Oh my gosh, 4 times. That was hard. And so you have 9 times 4. So that's going to give me, 36 plus 32. Okay. And so we get 8 and then 6. Okay. So 20 degrees is about 68 degrees Fahrenheit. So that's why I say that it could be a little bit warmer, like 22 degrees Fahrenheit or Celsius could be room temperature. Or you can recognize this. And likewise, to figure out if you have a temperature in Fahrenheit and you wanted to know what it is in Celsius, so let's plug that in. So 5 ninths into 68 plus, sorry, I need a minus 32 from that. And multiply. So 68 minus 32, well, that's 5 over 9. 68 minus 32 is going to be 36. 9 goes into 36 4 times. And then 5 times 4 is 20. It's like we recover, I should say. That if I gave you the temperature of 68 degrees in Fahrenheit, you could tell me what it is in Celsius by subtracting 32 from it and then multiplying by 5 over 9. Okay, so that's a relationship between those two and some common relationships that maybe you're familiar with. Okay, and here's an example of converting, which we just did. So you can look at this example as well, and then converting backwards. So I just did that example as well. So you can kind of see the relationship and making sense of it. And then finally, we have the Kelvin temperature scale. So this is the scale by which all things are kind of derived from, and where zero, what we call absolute zero, is when you're reaching 0 Kelvin, and that's considered kind of like the heat death of the universe. So at that point, then the universe would kind of cease to exist, or at least all living forms of it would be when the temperature reaches 0. You may have also heard about this in some situations with like super cooling things down to near absolute 0. What they're referring to is using lasers to cool like a system down to. Sometimes they can get into like really, really close to absolute 0, but you can never quite reach it. And when you get to really cool temperatures like that, some really strange properties start to happen. So to convert between Kelvin and Celsius, take your Kelvin temperature and subtract from it 273.15 degrees, and that will give you the Celtic temperature. Celsius, not Celtic. I'll give you the Celsius temperature. And then if you want to know what it is in Kelvin, you would undo that. You would add. So if you have if you had 20 degrees C, which is roughly room temperature, and added it to the 273, you would get to 93 to 9.15. And so that would be our temperature in the room in terms of Kelvin. Okay. And then so here's kind of like a relationship between them. So Kelvin starts at absolute zero and goes up. It doesn't have negative temperatures. Celsius, has zero at where water freezes, whereas Fahrenheit has 32 degrees there. And so the absolute zero in terms of Kelvin would be negative 459.67 degrees Fahrenheit, and Celsius would be negative 273.15 degrees. Okay. So it's kind of like the relationship of how they move up in terms of familiar temperature scales. All right. I hope that was helpful, and I will see you in the next video.